thermal fluid sciences experts. This is ProReadyEngineer.
Alrighty. Entropy. Entropy is a very interesting property. Engineering students struggle to understand it, and they have the right to. I do believe that very few people can actually educate engineers about entropy and what its value. So if you don't like it and you feel intimidated with entropy, you have, I can understand, I can relate. But it's actually not as bad as you think. Let me show you. Entropy is a property that is used to indicate randomness or disorder. A good way to think about it is if there is a lot of things are getting worse, entropy will increase. And when things are sorted out better, entropy decrease. The universe we live in as a universe, entropy is always increasing. Every single day is increasing. And this is why eventually there has to be a judgment day and death, and a day we're going to be taken back to the one who created us, because it cannot just be always getting worse and worse and worse. I mean, there will be some point where it has to come to an end. That entropy that measures disorder is extremely useful in quantifying how efficient machines operate. Let me tell you more. A very famous device is called compressor. You may have one sitting in your home that you use to inflate your tires. This compressor, the reason you have it is you're trying to add pressure to the air. Now, it's not going to do that except by pulling power from somewhere and then adding that energy to the air. Typically, you're going to plug it into your lighter. It has a battery. Put it in an outlet. It's taking electricity, then adding energy to air, and now you have energized air that you feed in your tire. That's a compressor. This is a compressor. Now, there's a reason that these compressors, when we depict them, when we plot them, we make it big here and small there. And we say this is one, we go from the big, we exit from the small. And what we are trying to do when we do this plot is a couple things. To say that it's compressed, like if you take a bottle, you empty that bottle, you stand on the bottle. The bottle will essentially compress and will reduce in size because it's compressible. So it will reduce in size and pressure will go up in your bottle. For it to compress, it needs work. It's going to withdraw work, power, so it can compress the air. There is something called irreversibilities. Irreversibilities are things that waste energy, and there's little you can do about it. You may be able to improve it, but you will not be able to eliminate it. It's friction. If you are trying to move a box in your basement, a very heavy box, 10 feet, and let's say you are pushing it on the ground, if you were moving it on a carpet is different than if you were moving it on bare floor, and different if you were trying to move it on wood. And in all cases, you're just sliding it over it. And all these differences come from friction. You wish there was no friction, then the pushing would have been much easier. The force that you need when there is more friction, you need to put more force. You know what's the only reason you're putting more force? And it's getting wasted. It's because there is more friction and that's it. You have to pay more than what you need to overcome this waste. If you get a compressor and all the target you need from the compressor is pressurize the air to me from 14 psi, atmospheric 14.7 psi, take it up to 100 psi. That's what I want you to do. If this compressor was ideal compressor, there is no losses, there is no friction, there is no secondary flows, there is no separation. Don't worry about these terms. They are actually very easy. Again, you understand, everything will be easy. But all what I'm trying to say is, if there was nothing, it's ideal, it's perfect. Let's say it was going to take 1 horsepower to give you what you want. If it was ideal, but it's not. So when you hook it up to your power outlet, it's withdrawing 1.1 horsepower. Why is it taking more? Should have taken 1 horsepower only. It's taking that additional power to compensate for the waste. And you end up with the 1 transferred to the air. Why are we talking about that in entropy? This is why entropy is needed. Entropy will quantify, gives you a method to quantify these losses because of inefficiencies. Let me show you how. This is called a state diagram. Again, you've seen it in my presentation. Here's H, enthalpy. You know that. Or it could be temperature. Why? Is it for air, H or T? You got it right, because H is equal to Cp times T. You can plot H or T. Would be very similar. Entropy on the x-axis. Here is P1, here is P2. Here is 0.1. What do you mean 0.1? Just ambient temperature. Here's ambient temperature, right? You go on this curve, you put ambient temperature, and you intersect ambient pressure. This is ambient pressure. So ambient pressure, ambient temperature, you give you a point. This point you have here, you've now identified a point on the state diagram. And from 1, we're going to move into a compressed state. So 1, right? If you have the compressor sitting right here in front of your eyes, right, on your desk, 1 is what's coming in. That's, we call this state 1. It's going to move to a state 2, and this is state 2 here. You see, if it goes with the entropy constant, this is S entropy on the x-axis is the same. S1 is equal to S2, and we say this is 2S, meaning 2 state 2, the exit of the compressor. Assuming entropy is the same, TS. This is an ideal compressor. This is the perfect compressor. It delivers, takes you from 1 to 2, and it doesn't change the entropy. It doesn't change the disorder. It doesn't have inefficiencies. It doesn't have friction. It doesn't have any of that. It goes from 1 to 2. S. Will you find this device? No, you won't. It doesn't exist. This device does not exist. What actually happens is you're going to go from 1 to 2 on this path. And 2, you're going to get the pressure you want. But 2 will be little warmer than 2S. And this is called 2R, like real. And you can just make it 2. Will be a little warmer. Why is it a little warmer? Because of all the things we said. Reality is entropy will increase. S2 is larger than S1. Oh, I hear you. I hear your mind. I'm reading your mind. You say, but you said it's gonna give me a measure of inefficiencies. Where is that? Now let me show you. This is called the compressor efficiency. How efficient is your compressor? It's actually a very simple concept. It's the work that is the best and least and minimal. You remember the example of the 1 horsepower? This is what you have needed ideally. This is what you needed ideally. Divided by what you actually sucked from the grid or from your outlet, or like the real work. You divide this by that, this is going to be a number less than 1. If it was 100% efficient, then your isentropic work is your work. They are the same, but they are not. What's going to happen is that your real work is more than your best isentropic best work. You see, work, I already told you, if you want to know this is your compressor and you want to know the work, it's actually very simple. See how the enthalpy changed from inlet to exit. Air was coming in with a certain enthalpy, 300. It's coming out with 500. What happened? Why did the air enthalpy change from 300 to 500? Because it sucked 200. That's it. Very simple. It's energy balance. In a separate presentation, I'm going to go over the details of energy balance on all machines. That will really enlighten you and makes it a very simple. Lots of complaints I hear from people on actually performing these simple energy balances. So we'll elaborate more on it. But for now, actually, it's as simple as I said. You see, air is coming in with $300. It exits with 500. What happened? Well, it took 200 from somewhere. That's as simple as that. And that work, right, is if you divide that work, this is if it was very efficient. See this delta? If you measure this delta, as if it was very efficient. But it's not that efficient. So it'd be this bigger delta. It's this bigger delta. And now you calculate your efficiency of your compressor, and now you say my compressor is 85% efficient. How were you able to know how efficient is your compressor? Through the entropy concept. Like here. Entropy concept allowed you by saying if the entropy was the same, this is the work. But truth of the matter, it's not. Now I have an efficiency. Now if you make your compressor go from 85% efficient to 87% efficient, great, to 89% efficient, awesome, 91, oh, you're doing better. I think right now the best we've reached in making of compressor is 95%. You can immediately know why would it be better, because you are improving from a friction standpoint, secondary flow standpoint, separation standpoint. We'll talk about that in a more advanced presentation, but here you go. Entropy allowed you to make a judgment on how efficient is the process. See, the entropy is beautiful. It's very nice. It really helps. It's great. Let's talk more about entropy. Entropy for a system doesn't necessarily have to increase or decrease. There could be a process that happens and entropy decreases in that process. Like you are removing heat, entropy will decrease. However, entropy of the system that is all inclusive of your surroundings will always increase. This concept may be a little bit difficult to digest, but not as bad as you think. Bear with me. You need the second law of thermodynamics. You see, the first law of thermodynamics is very easy. I already told it to you. It's energy balance. $300 coming, here's 500 exiting. What happened? 200 came somewhere. Is 500 coming? I'm exiting with 100. Well, you spend 400 somewhere. That's energy balance. That's straightforward, not a problem. That's first law of thermodynamics, energy balance. But what is the second law of thermodynamics? That's where the entropy comes into play. It says that entropy forces processes to happen in a certain way. It has to obey that. If you calculate the total entropy change for all your universe, and the word universe here meaning the system you are interested in plus everything surrounding it, it must be greater than zero. It will never be zero. It will never be less than, it cannot be less than zero. Let me give you an example. Here's a cup of coffee. That's your system. You are interested in the cup of coffee. It's hot. It's sitting on the table. Okay. How do I calculate delta S as the coffee is cooling down? S1 minus S2. You know, like you brought it, it was extremely hot. You put it there, you waited for 5 minutes, it's cooling down. There's an entropy change that happened. You will learn in thermodynamics that a simple way to calculate that with some assumptions is delta S is Q divided by T, right here. The Q, energy you lost, you know, when it's cooling down, you lose energy, right? Makes sense. Divided by the temperature of how hot it was. That's going to give you a delta S, and it's a negative. You know why it's negative? Because the entropy is dropping. It's getting better because you're cooling it down. Actually, entropy is dropping for the coffee. But the coffee is sitting on the table in your room. When it did that, if I ask you calculate the delta S of the room, you say, well, heat was added to the room. This is Q. And the room was sitting at a T cold temperature. That's T cold. No, the room is colder than the coffee, the boiling coffee that you brought. And that's the delta S of the room. If I tell you, give me the total delta S of your coffee and your surrounding system, the room, your universe, that delta S is greater than zero. Take a look again. It's the same heat transfer that you took from the coffee, you put in your room. But if you divide by a large number, T hot, the coffee was hot, this will be a small number. And the Q divided by the T cold, smaller number, this is a bigger number. Sum both up. That is going to be a positive number right here. Delta S is a positive number. So the generated entropy always have to be greater than or equal zero. In an ideal life kind of thing, it's zero, but typically it is not. So now you feel good about entropy. It allowed you to know how efficient your engines, your compressors, your turbines are, like we discussed here. And they taught you how energy has to flow in a certain way and obey that law. You see, you've heard about perpetual machines. And I'm amazed how many videos I see that are deceiving people. You know, there's no free lunch. Second law of thermodynamics say that things happen in a certain direction and they have to obey the order of that direction. Here is one video that say, you know, perpetual machines, like they tell you, you're going to put a rubber band here and a rubber band there, and then push the thing once and it keeps rotating forever. You've got power forever for free. This is a violation of the second law of thermodynamics. Inefficiencies and friction will make it stop. It will never continue forever unless you pay power. I have seen many people going for making an IP, intellectual property, and it's a shame. One of them was, he said, I'm going to bring a generator, a large mass, a dangling rod. You're going to push it, and then it will keep doing like this. And then we keep generating power. And I ask myself, did this person ever played with the pendulum? Did you hold the pendulum and let it go? And see it doing all this and fading away and stopping because of irreversibilities, because of the second law of thermodynamics, because it has to stop. And the only way to make your pendulum generate is if you keep pushing it with your hand, which essentially means nothing. You're just doing the work. All these things I said, there was another video of that guy. He said, I'm going to be driving my car, and he puts a fan on the car, a turbine, if you will. And if you are not comfortable with the term turbine, I think you are. You've seen those big wind turbines. He's putting it on his car, and he says, well, I drive the car. It's an electric car, and I put that wind turbine, and it charged my battery, and I'm driving for free. That violates the second law of thermodynamics. It's like you think there's a free lunch, and there is no free lunch. The energy that you are putting into the vehicle, you have to put more because you are actually the reason the turbine is spinning. Net balance is zero. In fact, you're going to lose more. Like if you do this exercise I just said, and you had to charge your car once every 5 days. So you add to it that device and you start driving it. You were charging every 5 days, is that right? You're going to charge every 4.5 days. It's going to get worse. Entropy says that. It says you have to pay extra for all the irreversibilities. You can't generate something from nothing. Enough for this concept, and let's move forward.